Every single law of indices you were ever told to memorize, including the scary ones with negative and fractional powers, is really just counting, nothing more. By the end of this video, you'll be able to rebuild any of these rules from scratch, on the spot, without ever memorizing them again. Let's start with a to the m times a to the n. Write a to the m out as a times itself, m times, and write a to the n out as a times itself, n times. Now just count every single a in that whole product, and you get m plus n copies of a multiplied together, so a to the m times a to the n equals a to the m plus n. Now let's stretch the same counting trick to open bracket a to the m close bracket to the n. That means you take the block a to the m and multiply that whole block by itself n times, counting up every lone factor of a inside all those blocks gives you m times n of them. So open bracket a to the m close bracket to the n equals a to the m times n. Now let's push our first law. A to the m times a to the n equals a to the m plus n until it almost breaks. Watch what happens as the second exponent shrinks. A cubed times a to the 1 equals a to the 4. A squared times a to the 1 equals a to the 3. Each time the exponent on the left drops by 1, the total on the right drops by 1 too. Keep going and you reach a to the 1 times a to the 0 equals a to the 1. For that to stay true, a to the 0 has to equal 1. Keep dropping the exponent past 0 into negative territory. We need a to the 1 times a to the minus 1 to equal a to the 1 plus minus 1, which is a to the 0, which we just showed equals 1. So a to the minus 1 times a equals 1, which means a to the minus 1 must equal 1 divided by a. Following that same pattern for any n gives us a to the minus n equals 1 divided by a to the n. Notice this is not a new rule, it is the exact same multiplication law, just carried past 0. Before we go further, here's a question for you to think about. If the rule a to the m times a to the n equals a to the m plus n still has to hold true, what must a to the 1/2 times a to the 1/2 equal, and what single number does that force a to the 1/2 itself to be? Pause here and make your prediction. Here's the reveal. Since a to the 1/2 times a to the 1/2 must equal a to the 1/2 plus 1/2, that's a to the 1, which is just a. So we need some number that when multiplied by itself gives a. But that is exactly the definition of the square root of a. So a to the 1/2 must equal the square root of a. It was never a special rule, it falls straight out of consistency. Now let's generalize that same argument. Multiply a to the 1 divided by n by itself n times, and by our very first law, the exponents just add up. N copies of 1 divided by n, giving a total exponent of 1. So a to the 1 divided by n multiplied by itself n times must equal a. And the number that, when multiplied by itself n times, gives a is by definition the nth root of a. So a to the 1 divided by n equals the nth root of a. Now let's put this machinery to work on standard form, also called scientific notation. Any number written as a times 10 to the n is really just an application of our very first law, since shifting the decimal point is nothing more than multiplying or dividing by 10 repeated n times. So converting between standard form and an ordinary number is just counting how many factors of 10 you're carrying. Let's convert an ordinary number into standard form. Take 340,000. We move the decimal point until we have a single digit before it, giving 3.4, and we count how many places we moved it, which is 5 places to the left. So 340,000 equals 3.4 times 10 to the 5. Each place we moved the decimal point was one factor of 10, exactly as our counting argument predicts. Now let's go the other way, converting standard form back into an ordinary number. Take 7.2 times 10 to the minus 3. The negative exponent tells us we are dividing by 10 3 times, which shifts the decimal point 3 places to the left. So 7.2 times 10 to the minus 3 equals 0.0072. Notice the negative sign in the exponent is doing real work here. It is not a trap. It is simply telling us which direction to count. So there you have it. Every law of indices, positive, zero, negative, and fractional all fell out of one simple idea: counting factors in a product. If this clicked for you, hit like and subscribe. And in the next video, we'll use this exact same counting logic to derive the laws of logarithms from scratch.